Okay, so this is the question we have discussed, the second one. The next one you see, an excess of liquid mercury is added to an acidified solution of this molar Fe3 plus. It is found that 5% of Fe3 plus remains at equilibrium at 25 degrees Celsius. Calculate E naught for this, assuming that the only reaction that occurs is this. Okay, so cell reaction is given and E naught of Fe3 plus to Fe2 plus is given. Okay. So you have to use Nernst equation here, right? This value, it should be E naught. It is just a misprint. This should be E naught. Okay. So now you see this mercury is getting oxidized and Fe is getting reduced, right? So cathode is what? Cathode is Fe3 plus to Fe2 plus reduction, and anode is Hg2 Hg2 plus. Okay. So E naught of this cell is what? E naught of cathode minus E naught of anode. Right? Here you see this E naught of anode, both are reduction potential, and that is what we need to find out, reduction potential. Means this E naught is the answer we have. Okay. Now when you apply Nernst equation into this, so E cell is equals to this thing, right? E naught cell is nothing but this. So E naught cell minus 0.0591 divided by 2, right? Because the n value is 2, log of Hg2 plus Hg2 2 plus into we have Fe2 plus square divided by the ion we have Fe3 plus square. This is what the equation we have. It says what? 5% of Fe3 plus remains at equilibrium. Means when this reaction takes place and equilibrium achieves, there we have 5% of Fe3 plus present in the solution. So obviously the state of equilibrium, E cell is 0, is equals to E naught cell minus 0.0591 by 2. We'll substitute the value of this. Log the concentration of Fe2 plus to Fe3 plus. So it is given 1%. So you see this thing we'll use over here. We have Fe3 plus, the reaction is this, concentration we can find out with this value. 5% thing is there. Okay, so see this. The reaction is two Hg plus 2 Fe 3 plus gives Hg2 2 plus plus 2 Fe 3 plus. This is 1 into 10 to the power minus 3 present initially. It is 0 and 0. When 5% left, mean 95% react, right? So this is the Fe3 plus concentration which is left here. That will be 0.95 reacts 1 minus, or we can write simply 10 to the power minus 3 into 0.05. Alpha is this, right? C minus C alpha we can write. So I can write down here. Suppose if I write down the general term, probably that will be easy for you to understand. If it is C initially and C value is given, so it is C minus C alpha. This will be C alpha. This will be 2C alpha. What is C alpha? C is 10 to the power minus 3 into 1 minus alpha. Alpha is 5%. So it is 1 minus 0.05. C is 10 to the power minus 3. Alpha is 0.05. 2 into 10 to the power minus 3. Alpha is 0.05. So this is 0.95 into 10 to the power minus 3. Right? This will be 0.05 into 10 to the power minus 3. This will be 0.1 into 10 to the power minus 3. Okay. Now we'll find out this concentration we have already. We'll substitute this and we'll get the answer. Okay. One more thing you see here. One thing we must write. This is one thing I'm missing here. Just one small correction here. You see, this should be 2C alpha, no? Because 2 we have here. 2C alpha. So this will be what? This will be 2 alpha. 2 alpha is 0.1. So this is the concentration we have. Now when we substitute all these value here, and we'll find out E naught cell, right? So E naught cell here is, we can also write this down as E naught cell is equals to, it is E naught of cathode minus E naught of anode. And that would be equals to, when you solve this, we'll get some value here. So E naught of anode we need to find out, which is Hg2 plus, right, reduction potential. So E naught of anode is equals to, the value we get is 0.7926. This is the answer we get in this question. Okay. So what we are doing here, we are just using Nernst equation. Equilibrium condition will apply here. And then to find out the concentration of the species involved, we use the concept of equilibrium, right? Ions are in equilibrium. So how it dissociates, how concentration of ion changes, we'll find out that and we'll substitute it in this. We'll get the expression. Okay, fine. Okay, now you see the next question. The standard reduction potential of copper is given 0.34, right? Standard reduction potential of copper is given 0.34. Find the reduction potential at pH 14 for the above couple. KSP is given, right? So we need to find out the reduction potential of Cu2 plus to Cu. KSP is given. So KSP is given for CuOH whole twice. So CuOH whole twice dissociates as Cu2 plus 2OH minus. So KSP expression, if I write down, that will be concentration of Cu2 plus concentration of OH minus square, right? So if it is S, this one is 2S. So we can write 4SQ. So concentration of Cu2 plus is equals to S is equals to KSP by 4 root over of it. And that would be 10 to the power minus 19 divided by 4 root over of it. Okay, so this is one more thing is given, pH is given, right? So it means POH is what? POH is 0, means OH minus constant. Okay, fine. We can do this way also. Right? Because why we cannot use this, I'll tell you. Because the solution pH is given, means its OH minus concentration is already given. Means in the solution we have H plus OH minus already present, right? Hence we cannot talk about the solubility of this, right? This solubility we get when there is no common ion, but when common ion is present, the solubility is something different, right? So this is true when the solution does not have any common ion with respect to this salt, right? Hence we can not use this method over here because the solution we do not have any idea about the solubility of this compound since solution thing is not mentioned. KSP expression is this, but we know the fact that when pH is 14, it means POH is 0. This means OH minus concentration, if you find out, that is 1. And hence 1 we substitute here. So concentration of Cu2 plus we can find out with, that is 10 to the power minus 19 with the given data. Okay. Now we can use Nernst equation and find out the answer, right? Nernst equation for Cu2 plus to Cu, we can write E Cu2 plus to Cu is equals to E naught is 0.34 minus 0.0591 by 2 log of 1 by Cu plus. Okay, all the value you can substitute here. 0.34 minus 0.0591 by 2 log of 1 by Cu2 plus is 10 to the power 19. So when you solve this, you'll get it as around minus of 0.22 volt, right? This is the answer for this question. Okay, so the point here, we won't use because ultimately we have to find out the concentration of Cu2 plus, but we won't use the solubility expression here. Why? Because the pH of the solution is mentioned, right? So there is H plus present into the solution, and in presence of H plus OH minus, the solubility may differ, right? That's why we cannot use that KSP is equals to S4S square, 4S cube expression here, okay? Hence, we'll find out the OH minus concentration with respect to pH, which is this, and then KSP. Okay. Now, the next question you see. How many grams of silver could be plated out on a serving tray by electrolysis of a solution containing silver in +1 oxidation state for a period of 8 hours? Okay. So obviously, when electrolysis is there, the question is based upon Faraday's law of electrolysis. Time is given 8 hours. So 8 into 60 into 60 seconds. Right? This is the time. I is given. I is also 8.46 ampere. What is the area of the tray if the thickness of the silver is plating is this centimeter, right? Area of the tray. So see, density is given. Density is given. With density is equals to mass by volume. Volume is equals to what? Area into the thickness. Right? So area we need to find out. Thickness we know. Mass, we can find out the mass which deposit, and density also we know, right? So first of all, we'll find the idea of behind this question is what? We'll find out the mass deposited, that is M. So mass is what? Mass is equals to density into volume, and volume further we can write density into volume, further we can write area into the thickness, that is X, suppose we have. Okay, this area we need to find out. So area is equals to what? Mass divided by density into the thickness X. Okay, so density is given, thickness is already given, right? We need to find out mass. Now for mass, what we can write, M is equals to EIT by 96500, right? E is the equivalent mass, and that would be 108 for silver. +1, so it will 108 only. I is 8.46, and T is 8 into 3600. This whole thing is divided by 96500. Okay. So you can calculate this, and we'll find out mass. That mass would be approximately 272.17 gram. 273 also you can take, approximately this. Now this mass will substitute here, 272.17. Density is given 10.5 into the thickness is 0.00254, right? So area is 1.02 into 10 to the power 4, and the unit is centimeter square. This is the answer for this question. Easy one. Okay. Next question, you see. The electrolysis of a solution of MnSO4 in aqueous sulfuric acid is a method of preparation of MnO2. Okay, what is said? That electrolysis of a solution of MnSO4 in aqueous sulfuric acid is a method of preparation of MnO2 as per the reaction given. Passing a current of 27 ampere. Okay. So I is given 27 ampere. T is 24 into 3600 seconds, right? Mass of MnO2 is 1 kg, means mass is 1000 gram. Okay, we need to find out the value of current efficiency. Okay, now for all these things, we know we have to apply Faraday's law of electrolysis. M is equals to EIT by 96500. We'll find out current for this. What is the current required for this particular mass to get deposited? 1000 into 96500 divided by E into T. T is 24 into 3600. What is E? E is the equivalent mass. So that would be atomic mass of manganese, and the change is what? The change is of, you can see here, the number of electron exchange is 2. Okay. To balance this, you get 2H2O plus side. Plus 2 electron, correct? So if you write down this reaction, I will tell you how do we get the number of electron exchange. Mn plus 2 converts into MnO2. So when you balance this in acidic medium, we'll write 2H2O this side, then 4H plus this side. When you balance the charge, we have to add 2 electron this side. Okay, so charge will be balanced both sides. 2 electron is getting exchanged. This will be atomic mass of manganese divided by 2 equivalent mass. So when you solve this, the I value that you get here is 25.67 ampere. Okay, so current efficiency is what? Current efficiency is the current that has been used divided by the current which is provided into 100. When you solve this, you'll get approximately 90% current efficiency. Got it? Next one, you see, calculate the equilibrium constant for the reaction. This everything is given, right? Equilibrium constant means what? Delta G is 0, so we can write delta G naught is equals to 2.303 RT log Kc. This Kc we need to find out. Okay, what is the E naught of this cell? Because delta G, we know it is minus NF E naught of the cell is equals to 2.303 RT log Kc. So this we can further write the number of electron exchange is 1. So log of Kc is equals to minus N divided by 2.303 RT by F. So log of Kc is equals to into E naught cell. So log of Kc is equals to 1 divided by this value is 0.0591 into E naught cell is, see, Fe is getting oxidized, Ce4 plus is getting reduced, right? So Ce4 plus to Ce3 plus, Fe3 plus to Fe2 plus. So this is cathode and this is anode. So E cathode minus E anode. So E naught cell is 1.44 E cathode minus E anode. The reduction potential of this 0.68. Okay, this is the E naught cell. That will be 6. Point 76 volt, which we substitute here. Kc value is 6. Okay. I have missed a sign here, minus. So this minus gets cancelled. This is the answer we get. Okay. So answer for this question is 7.6 into 10 to the power 12. Okay. The next question is, find the solubility product of a saturated solution of this in water at 298 Kelvin if the EMF of the cell is this. Okay. So this is Ag to Ag plus and this is this, correct? Ag plus to Ag. So this side we have cathode and this side we have anode. Okay. So for this reaction, if I write down the E cell is equals to E naught cell minus 0.0591 divided by 1 log of Ag plus cathode by Ag plus anode. This is what the reaction we get. Now, Ag plus cathode, the concentration is given 0.1, right? Since we need to find out the solubility product, so we have to find out the concentration of Ag plus in the anodic side. So if I substitute all the value, E naught cell is 0. It is a concentration cell. So E naught cell is 0. 0.0591 by 1 log of 0.1 by the Ag plus concentration on the anodic side. Now, when you solve this, you'll get the concentration of Ag plus at anode, and that is 1.66 into 10 to the power minus 4 molar, right? So when you look at the dissociation of the salt, which is Ag2CrO4 here, Ag2CrO4, it dissociates as 2Ag plus CrO4 2 minus. Okay, the concentration of this is 2S, which is given here. We have already calculated, and this is S. So with this relation, you see the concentration of CrO4 2 minus, if you calculate O4 2 minus, that will be the half of this divided by 2, half of this. Now the solubility product KSP is equals to, we have 4S cube, right? S value is this. So answer is 4 into 1.66 into 10 to the power minus 4 divided by 2 cube. So this is 2.287 into 10 to the power minus 12 mole per liter. Okay, this is the answer. Okay, I can understand, guys, there are some calculation into this, some log, anti-log value must require to solve this kind of expression. But these are the questions. You can see these are questions of 1998. There we have this kind of calculation. We have JEE screening and mains exam that point of time, and we have subjective questions also. So we get enough time for this kind of questions there. Okay, so that's why they give some weird kind of calculation also in the question. But nowadays you don't have that much time, right? So you won't get calculation also like this. But the concept you must understand how to do this kind of questions. Okay, so fine, guys, thank you. We are done for the session for today. Okay, see you in the next session. Take care. Bye bye.